we have an equation for friction. Put that in. Fgx minus the frictional force is always times the absolute value of the normal force. No mass, the mass is 10 kilograms, times the acceleration in the x direction. All right, so if we just knew what that was, we'd be okay because that out over here. Got to figure this out. Got to figure this out. And if we knew those two things, fuzzy. Let's go up and look. Taken weight broken into components. Weight is always mass times the acceleration due to gravity, assuming this box is on Earth. So we actually know both. We know that the mass is 10 kilograms. The acceleration due to gravity is second. So the weight is actually just 98 newtons. This is rather handy to us because we know that these are the components of that. This is a right triangle, 30, 60, 90 right triangle. We can write relationships to find these other things. Sine 30 degrees, opposite side is Fgx. The hypotenuse is 98. Cosine of 30 degrees equal to the adjacent side, Fgy, divided by the hypotenuse, which is 98. Pulling up my calculator. Oh, I don't need my calculator for this one. Sine 30 is 1/2. Half of 9.89. So Fx is 49 newtons. Fill that in over here. Fgx is 9. I do need my calculator for this one. Don't really care to deal with exact values. I want to go to approximate decimal value. 98 times trig sine 30 degrees is so. Oh, focus is really bad. I apologize. I'm not sure what to do with that. So we have Fi equal to 4.9 newtons. Fill that in. Newtons. So look, apparently F of n, or F sub n, is 4.9 newtons as well. Fill that in over here. All right, so we're actually in pretty good shape here. The question becomes, this box moving or not, so that we know which of these two values to fill in for our friction. The idea here is that we choose the bigger one first. We try static. If we put static friction in here, the result tells us that the box should accelerate up the hill. Well, that's nonsense. Of course the box isn't going to accelerate up the hill, so we know that that's wrong. So if this 49 is larger than our force of friction, static-wise, then it will accelerate down the hill, at which point we know it's not moving, or it is moving, so the static friction doesn't work. So we're going to try the static friction first. Put in 0.4, see what happens. 49 minus 4 times 0.9 gives us a value of 15.04 newtons. equals 10. It looks like we should just be able to charge forward, but we actually can't. All this tells us is the object is moving. Because the object is moving, the wrong number here. So we again putting in 0.2 in that place. This, while it was useful, we're going to ignore that. We're going to change this to 0.2 because it's clear that the box is actually moving. Calculate 49 minus 0.2 times 4.9. That gives us a larger 2 newtons, 10 kilograms times the acceleration in the x direction. I can handle that division. The acceleration direction is 0.2 meters per second squared. Now it feels like we should be done. We haven't actually answered the question. The question wants to know, how long will it take to get to the bottom of the ramp? Well, we don't know, but we do know that it is accelerating, and we do know the direction of the acceleration. Take a moment to explain why we made this choice. We made the x direction the surface so that we wouldn't have to worry about the acceleration in the y direction. We already said right here that the acceleration in the y direction, 0. This simplifies our life quite neatly. So we're going to go over to the next page here. I'm going to start with what we know. We have this box going down a ramp. We know some stuff. We know its initial position, 0. We know its acceleration is 3.2 down the ramp, which we're going to go ahead and call positive. We know its initial velocity was 0. That was given in the statement of the problem. Start time at 0. The box is going to ultimately slide down to the bottom. At that point, its position is 2 meters. Acceleration will 0.2. The velocity will be, don't know the time. That's actually what we are looking to find. Great. So let's go figure it out. We have a one-dimensional problem. Let's look at our velocity time graph. We know the initial velocity was 0. We know that it is speeding up. It has an acceleration. Slope is 0.2 meters per second squared. Acceleration is the slope of the velocity time graph. We know that the area under here, at TF, the time we're looking for, we know that this area is 2 meters. So let's write out all we know. We know that the velocity at any time is 0.2 times the time plus the initial velocity, the y-intercept, at 0. And we know that the displacement equal to 2 also equal to the area of a triangle, which is 1/2 base times height. Okay, well, half the base of my triangle, TF. The height of my triangle is the velocity at TF, which we call VF. So that any velocity we want is given to us by this relationship. So VF, velocity at TF, is simply 3.2 times TF. Substitute VF, this in 1/2 TF times 3.2 TF.